Okay, good evening. My name is Deepa Venkitesh, and I'm here today with a talk on understanding laser phase noise as a part of GW at home. The picture that I've shown you here is that very familiar picture of LIGO interferometer. Is just a schematic of the LIGO interferometer, and you see that there is a source of light, and this is a Michelson's interferometer. So you have light split into two arms, and as a result of the gravitational wave propagating through this space-time, what happens is the length of these arms increase or decrease, and so the phase experienced by the light as it counter propagates through these arms change, and we are recording our information in one of the dark ports of the interferometer, and you look at the intensity changes in that port and then identify the nature of the gravitational wave. I mean, this is a very simplistic explanation of the detection process in the gravitational wave. So the key part in this experiment, in this mega experiment, is this laser source. And we are trying to spend some time today to understand the noise. It's not just the phase noise, all the noise sources of this laser. So here's the outline of the talk. First, we will talk about coherence and what are the coherence requirements for interferometers. I'll give you a very basic working principle of laser. Then we will talk about the non-idealities of the laser, which are intensity noise, line width, and phase noise. Then we will spend some time on why the laser noise becomes an issue in interferometer, especially in a LIGO interferometer. And we will also spend some time on the measurement of intensity noise and phase noise. So before I start, I will let you know that this is going to be at a very elementary fundamental level, aimed at undergraduate students. So experts there, please bear with me if the material is sounding very elementary. Also, unlike the other talks, I would like to take a break at about 15 to 20 minutes. So please keep typing your questions, and at the end of 15 minutes, we will stop, and 20 minutes we will stop and take your questions before we go on further. So talking about coherence. So this is a term that you have heard from high school. And when we talk about coherence, there are two classes of coherence you talk about. You talk about spatial coherence, and you also talk about temporal coherence. What is this idea of spatial coherence? It becomes important because it's a free space interferometer, so you need to worry about spatial coherence of the laser. So spatial coherence, as this figure indicates, so this is an example of a wavefront. It is not really a plane wavefront, but wavefront with some random distribution, random shape. But the coherence, spatial coherence would mean that if I consider 2 points x1 and x2, that's marked here, x1 and x2, which are at two different spatial locations in the wavefront. Now, if the ability of these 2 points to interfere when the time is averaged, that's spatial coherence, and that's quantified through coherence length. So let me explain what I mean. So this is a wave front of the first wavefront is that of infinite coherence length, which means that or maybe we should look at the finite coherence length case in this case, for instance. So you see from, you have a point here in space, and you have another point in space. For this length of time, you will see that the coherence is, so in this area, if you look at, the wavefront shape remains the same over the coherent area, right? So that indicates the spatial coherence. Now, a good way of understanding the spatial coherence and its ability to interference is, let's say that the wave is combined with a copy of itself. So you have a red wave and you have a blue wave. And let's say the coherence length is infinite, right? Which means that along the space, the phase relation is maintained all along. Now, this is a classic example of what happens in the Michelson's interferometer. You have the beams coming from both the arms, and you will combine with a beam splitter, and you will see the dark port. So this is the source, and so this is what happens in the detector here. So you can imagine that these two, red and blue, are coming from the two arms of the interferometer. Now, if these two arms, this particular example shows that they are coherent, they have infinite coherence length, but there's an infinite coherence area also, but they are not aligned with in space. So this is an example of a misaligned interferometer. It is coherent, but it is misaligned. So as a result of that, the net intensity that the detector will detect is not really maximum if you're trying to maximize. So you can use this information to kind of align the two mirrors to make sure that the interference that you get is maximum. So the way you quantify the spatial coherence is through what is called as a coherence length, right? So coherence length tells you the distance up to which the wavefronts remain coherent. And this is again a statistical quantity. Now, let's move on to temporal coherence. Now, temporal coherence tells you how monochromatic the source is, right? So here it's a laser source. So we know that the laser emits single color. And when I say single color, does it mean really only one wavelength or one frequency, or is it a spread of frequencies, right? So the measure of how narrow is the emission of light, how narrow is the emission of light is the temporal coherence. Now, if you have a pure sinusoid, if it is extremely monochromatic, it means that the wave can interfere with itself at a different time, and at any time if you interfere, the answer is going to be the same. So for instance, this is on the top, you have a wave which is of infinite coherence time. And what you see on the x-axis is actually the delayed version of the same wave. And you see that the phase relation between the blue and the red is always maintained, right? Here also, this is a specific delay. I mean, at this delay also, there is the phase difference is pi. And that is maintained irrespective of what the delay between the two waves is. Now, what you show, what is shown here at the bottom is an example where the wave is not where the coherence time is not infinite. This has a finite coherence time. Okay? So you see a red wave, and you also see a delayed version of the same wave. And what it shows is that at the beginning of the delay, you see that the amplitude of the waves are matching. But at the same time, as you keep increasing, as the wave propagates, as you keep increasing the delay, you see that the delayed version is slipping. The delayed version is shown in red. That is slipping in phase. And after a certain time, coherence time, what you see is that they are going completely out of phase. Right? So this is a visual picture of how time coherence can be quantified. Another way of visualizing this is, let's say you're able to capture this wave in an oscilloscope, and you're just marking every zero crossing, right? Whenever the wave is crossing zero, you're just drawing a line. Again, next time when the wave is crossing zero, you're drawing a line. And you're trying to superpose all those lines in the same window. Right? So this is what that picture would look like, right? Gradually it is slipping off, and that zero crossing will keep changing. And it means that, so you're superposing every cycle on top of each other. You will see that the zero crossing keeps changing, right? Which means that the phase keeps changing, right? So what is the consequence of this phase changing? How do you quantify that? The way it can be quantified is through the frequency spectrum, right? So that we come back to the same example. This is a pure sinusoid. In the frequency domain, it is a single frequency. So I'm taking only the positive frequency component. If you actually do a Fourier transform, you have a positive frequency and a negative frequency. But I'm talking only about the positive frequency. And we know that the Fourier transform of a sine wave is a delta function, which means that it has only one frequency associated with it. That's a way to physically understand that. And that frequency is decided by the number of cycles per second and so on. But in the picture here below, what you see is a capture of the sine wave. So I have actually shown this example where 3 cycles of sine wave are captured and they are superposed on top of each other. So the sine wave is just propagating, but you're just folding the sine wave back. And you see that, as I showed earlier, the zero crossings are continuously shifting in time, which means that the phase is continuously changing. Now, if you take the Fourier transform of this kind of wave, what you will see is that in the frequency domain, you no longer have, you of course have a peak at corresponding to the frequency of your sine wave, but you no longer have a delta function. All these zero crossings will, a physical way of understanding is the frequency is the derivative of the instantaneous phase, and at the instantaneous phase at any given instant of time, this derivative keeps changing, and that gives rise to a spread in the frequency domain, right? So an incoherent light is characterized by a spectrum which is broad. And now the nice thing is, just by measuring this spectral width, you can quantify the coherence time, which is approximately 1 by delta f. I'm saying approximately 1 by delta f simply because depending on the shape of this, whether it is a Lorentzian or a Gaussian, you will have some small factors that are coming in here. Let's not get into the details. But what I can tell you is that the coherence time is related to 1 over delta f, whereas coherence length is the length duration of time over which this coherence can be maintained. And so it is nothing but speed of light times the coherence time, right? So if you can get the information in the spectrum, that is a measure of temporal coherence, and also you can now get an idea of what the spatial coherence of light is. Now, laser is that source of light which is coherent. We know that. So we need to have a source of light which is spatially and temporally coherent. Why do we need to have a source of light which is spatially and temporally coherent? In any interferometer, or especially in a LIGO kind of measurement setup, we are interested to measure the phase fluctuations that are caused by the perturbation. In this case, gravitational wave. We are really not interested to measure the phase perturbations caused in the laser here, or in the spatial coherence case. We are not interested to measure the spatial variations because of the changes in the phase wavefront, right? So we are not interested to measure the characteristics of the source. We are interested to measure the characteristics of the perturbation, and hence, you want to minimize all these fluctuations in time and fluctuations of phase in space, so that your measurement is now dependent only on the perturbation. So you need to have a source of light with extremely good spatial coherence and extremely good temporal coherence. And what we know is that laser is one classic example of a light source which exhibits spatial and temporal coherent properties. Now, having said that, you would have learned in your high school that laser is a monochromatic source of light, it is a coherent source of light, and so on. But depending on how you build the laser, what goes into the design of the laser the spatial and temporal coherence need to get, or the value of the spatial coherence and temporal coherence would be different. And whenever we make a laser and we say we use it in an interferometer, we need to say what exactly is, how do we actually quantify this spatial and temporal coherence. So just a primer on laser to understand why laser can give you a coherent source of light. Any laser, the light that is emitted from a laser is because of a light matter interaction. And if you go back to the basics of light matter interaction, there are three processes possible when light interacts with matter. The first process is absorption, where you see that you excite the system with photons. It will result in the absorption of atoms, electrons, ions, depending on what system you're considering. That would get into the excited state, and you typically don't have any emission of light. This is just absorption that happens in the system. The energy that is absorbed is used to excite these ions to higher energy states. The de-excitations may be just thermal. You don't get any light out of it. This is one example of absorption, light matter interaction. But the interesting example for light matter interaction we are dealing with in optical sources is the process of spontaneous emission, where you don't have to excite the emitter with anything. So nothing goes into the system, but the electrons, ions, molecules which are in the excited state. Why am I saying electrons, ions, molecules? Depending on what kind of medium you are using. For instance, if you're using a helium neon laser, it is the neon atoms that will get de-excited. Similarly, depending on what laser system you're using, it could be electrons. If it's a semiconductor system, it is electrons. Depending on what kind of gain medium you're using, you could have different, particles, if I can call that way, which results in which moves from the higher energy state to the lower energy state, resulting in emission. And in case of spontaneous emission, you typically don't excite the system with light. Of course, you can create this population in the excited state with a light source. We are not talking about that. So you can pump the system such that, of course, the ions or electrons would require energy to get into the excited state. So assume that they get that energy either electrically in case of semiconductor lasers or optically in case of optically pumped lasers. What happens is, in the absence of incident photons, these electrons or ions de-excite randomly, spontaneously. Spontaneous actually means on its own, right? So there is no correlation between the photon that is emitted by the first ion with respect to the photon emitted by the nth ion, resulting in incoherent light. So this is spontaneous emission. Now, in stimulated emission, what happens is you have the ions in the excited state, right? But now you have the incident photon that stimulates the de-excitation between the higher state and the lower state. And when that happens, you have all the ions, all the photons that are emitted, they get emitted at the same time, and they are coherent with respect to each other. This is a very simplistic way of understanding why laser generates coherent light. So I will break here. Of course, I can break here after saying that, of course, this is the process of light amplification by stimulated emission of radiation, or the laser. And this can give you monochromatic coherent source of light. It is monochromatic because all the transitions happen between the two given energy states. So the frequency generated is given by this delta E, if delta E is the spacing between the energies, and all the ions, all the photons are emitted at the same time, or coherent with respect to each other, and that's what is giving you coherence. So in the topic A, which was about coherence, I have a question here. Tanmay has asked a question. Frequency, one frequency or zero frequency? Question is not clear. Oh, I suppose. Okay, let me go back to that slide and try to explain what that was. So if you have any questions on this topic up to the first 15 minutes, you can shoot it. Probably it was related to this slide. So it's actually intuitive to understand the time frequency domain pictures so that you can correlate what is happening. So suppose I have a single frequency. So let me call this as a sine omega naught t, or sine 2 pi times 1 hertz, right? Frequency times t. Right? So this is a example of a sine wave where I know the frequency is 1 hertz, which means that from here to here, to complete one cycle, the time taken along the x-axis is 1 second. Now, I can think that in the Fourier domain, you have only a single frequency. There's only 1 hertz that is present in the system. So I have only one frequency, which is a delta function that is present. So this f is equal to 1 hertz in the example that I have chosen. Right? I hope so that single frequency idea is understood. But now, if you have waves which have, the timing, the phase is uncertain, you know that the frequency, this is again an intuitive way of understanding, frequency is, or f is d phi by dt. Right? Its instantaneous derivative of the phase is frequency. So if I, at a given zero crossing, for instance, right, I keep finding out what is the derivative of the phase. So for example, this wave is at a phase 0, for instance, but this wave has a phase which is not 0, it is becoming 0 only here. So if I take the derivative of this with respect to time, that is not going to be that is not going to be 1 hertz, right? So there is a spread. And that's what I said, that whenever you have, in RF, you call it as timing jitter. Whenever you have a timing jitter, it results in the phase spread. So I hope that answered the question. Nadia has a question. For spontaneous emission, how do we get the ions to the excited state in the first place, right? So that's a good question. We definitely need some other mechanism. That's what I marked here. We definitely need some other mechanism to get these ions into the excited state, right? It's just that the de-excitation, so for both spontaneous emission and stimulated emission, you need the ions in the excited state. It's just that in spontaneous emission, the de-excitations are happening in a spontaneous manner on its own, and hence they are uncorrelated. Whereas in stimulated, in fact, the rate at which this happens is decided by the lifetime of the excited state. So lifetime is the time taken, or the time after which 1 by E of this population, so let's say the population was N naught, the time after which 1 by E of this population gets de-excited is the lifetime of this state. And depending on its lifetime, these ions will just get excited statistically, and they are not in correlation with each other, and hence the light is incoherent. Okay, so the questions are done for now. So we said that, so we kind of very intuitively understand that in stimulated emission, the whole process is initiated by incident photon, and hence all these de-excitations are in unison, if you can think that way, and hence the light is coherent. So we will move on. Again, I can warn you that this was a very simplistic picture of laser. In order to actually understand this, we have to get into the laser theory, and maybe we can have another talk on details of how a laser works. The important point to note here is that in a system where you have spontaneous stimulated emission, it doesn't mean that the spontaneous emission does not exist. So the key take-home point here also is that out of the N ions in the excited state, a majority of these ions would get de-excited because of stimulated emission, but there is still a small fraction of light, small fraction of photons which get de-excited on its own. So there is spontaneous emission even in the presence of stimulated emission, right? Which means there is some amount of incoherence even when you get coherent light. And this is an important concept to take forward. So how do you make a laser? So you make you pick up a gain medium which has spontaneous emission or stimulated emission capability of emission. You pump it so that you can excite the ions to the excited state. So this pump could be optical pump in an optically pumped laser, or in an electrical pump in a semiconductor laser, and so on. For example, in a ruby laser, it is a flash pump. In all the lasers that are used in LIGO, it is again an optical pump, right? So that pump simply means that it provides a large amount of energy for the ions to get excited in the excited state. And of course, stimulated emission happens when, it can happen when the lifetime of the excited ions, lifetime of the state, corresponding state is high, so that you can kind of accumulate all the photons there, or all the photons are allowed to occupy that state for a longish time. They don't undergo spontaneous emission very fast. And then you can come in with an external photon. And this external photon should have an energy h nu, which corresponds to this band gap. So the question is, where do you get that external photon to create this stimulated emission? So what you can do is that any typical laser structure will have a cavity, which are simply mirrors. So you have the gain medium placed between two cavities, two mirrors, and a spontaneously emitted photon is getting reflected back into the system with the mirrors. So it could spontaneously emitted photon could go in any direction. So the photon that got emitted in this direction got reflected back into the system, and that is what is creating the stimulated emission. And we talked about spatial and temporal coherence. So the spatial coherence property of the laser comes from the fact that in space you have confinement in the cavity. The cavity supports specific transverse mode profiles for the laser, and that gives the spatial coherence. And of course, the spontaneous emission decides the temporal coherence. So the larger is the spontaneous emission, the lesser is the coherence, right? So you want to have the stimulated emission rate to be larger than the spontaneous emission rate, so that you get a better temporal coherence. Now, what could be the gain and phase conditions in a laser? So this is an example of a cavity. This is a mirror, two mirrors arranged this way forms what is called as a FP cavity or Fabry-Perot cavity. Previous LIGO talks would have told you that even the Michelson's interferometer also has a Fabry-Perot cavity inbuilt, but that's for a different purpose, right? So that is to increase the circulating power in the Michelson's interferometer. But here we are talking about a simple Fabry-Perot cavity that constitutes the laser. So let's say there are two mirrors whose reflection coefficients or reflectivities are R1 and R2. R1 simply means that of all the power that is incident on it, R1 fraction gets reflected back into the cavity, right? And let's say that the gain in the system is G in Neper per meter, and the loss in the system is alpha in, again, Neper per meter, because system could have losses as well. We are trying to write the condition for sustained oscillation. So this is like your Burghausen's condition in an electronic oscillator. This is nothing different from an electronic oscillator. In an electronic oscillator also you have a feedback, and here the feedback is given by mirrors. There it could be a resistor capacitor pair and so on, right? And for sustained oscillation, we are trying to say that the gain is approximately equal to loss for sustained oscillation. And it is not very difficult to write down this condition, because you say that, let's say A naught represents the amplitude of the electromagnetic wave at the beginning. So at t equal to 0, you have some electric field here, and you're trying to track what happens to that electric field in one round trip. So you see that at the Okay, let's change the color. So you see that after one round trip, so the wave gets traversed this way, it gets propagated this way, and it comes back to the same position, right? So I'm trying to find out what is happening to the electric field. It is A naught. It gets reflected in the two mirrors. The power reflection coefficient is R1 and R2. So the field reflection coefficient becomes square root R1, R2. There is the whole field actually takes twice the round trip in the system. So the distance covered is 2d, which is why e power minus alpha 2d. So alpha is a Neper per meter, so the loss becomes e power minus 2 alpha d. And similarly, there is a gain, so there is e power 2gd, because this field also experiences the gain. And you also have to remember about the phase, because if I assume the electromagnetic wave is of the form E naught e power j omega t minus beta z, this is the general representation of an plane electromagnetic wave, the propagation phase is beta z, and because the z is twice d, you have minus j 2 beta d. So the condition we are imposing is that the field that started here and the field after one round trip has to be identical. It cannot keep growing, nor can it decay. Because if it grows or if it decays, it means that there is no sustained oscillation, right? So you're just demanding that A naught is equal to this. So this would mean that there are two conditions to be satisfied. If you look at it carefully, there is a phase condition and then there is an amplitude condition, right? So the amplitude square root R1, R2 e power minus this part should become 1, so that this A naught is equal to A naught. And this part should also be 1, which means that this 2 beta d must be a multiple of 2 pi. So if I write those condition, the gain condition, this part, which is square root R1, R2, and this exponential term is 1, it means that I need a gain of at least this number so as to compensate for all the losses in the cavity. So that gives you the threshold for a laser. So this tells you, this is the intuition of why a laser always has a threshold. So you need to give in enough energy into the system so that there is enough gain to compensate for all the losses, right? And once this threshold gain is achieved, the gain is actually locked into the loss of the system. It becomes, it's actually get clamped at the loss of the system. Now, what does the phase condition tell you? As I discussed earlier, 2 beta d must be equal to a multiple of 2 pi. And beta is nothing but the propagation constant. And the propagation constant is 2 pi times the frequency divided by c, and c by n, because there could be a medium here of refractive index, right? So this is beta, and this must be equal to m times, okay, there is a d missing here, sorry, m times 2 pi. This gives you the allowed frequencies of in the system. So if I rewrite this, I get the allowed frequencies are m times c divided by 2nb, which means if I take a cavity which is, let's say, 1 centimeter long, and I have a refractive index of, let's say, 1.5, this allowed frequencies are m times 3 into 10 power 8 meter per second divided by 2 times 1.5, which is 3, multiplied by 1 centimeter, which is 10 power minus 2 in meter. This gives me a number m times 10 into 10 power 9, which is m times 10 gigahertz, which means only those electromagnetic waves whose frequencies are multiples of 10 gigahertz are supported by this cavity. Right? So if I were to draw the frequency spectrum of, or the transmission spectrum of this Fabry-Perot cavity, it simply means that right from 0 frequency to all those frequencies, there is no limit for this m, all those frequency whose separation is 10 gigahertz is allowed by this Fabry-Perot cavity, right? So if I have a gain medium whose emission spectrum or the emission band of the gain medium is, let's say, if the emission band is, for example, like this, right? This is the emission spectrum of the medium. And let's say that emission spectrum is centered at some 100 terahertz, corresponding to, or 180 terahertz. This corresponds to visible light, right? And if you can choose a 1 centimeter cavity, and if this gain spectrum is, whose width is less than 10 gigahertz, it means that only one mode, one longitudinal mode, gets supported by the system, which means that the output spectrum will look like this. Suppose my gain emission spectrum of my gain medium is really broad, right? I pick a gain medium where you have in the upper state and the lower state are really broad, so that the emission is really broad. It means that I can have the laser whose output is going to look like this. The spacing between these allowed frequencies are given by this Fabry-Perot condition, resonator phase condition of the resonator. In this example, it is 10 gigahertz, right? And this envelope is decided by the gain spectrum of the lasing medium. Now, this is what happens in a Fabry-Perot laser. Now, what would you require for a LIGO laser? The LIGO laser should not definitely have multiple frequencies. You want only single frequency so that it becomes coherent. So you need to, first of all, maintain a condition of what is called as single longitudinal mode laser. You need to have what is called as a single longitudinal mode laser, or SLM, single longitudinal mode laser, so that there is only one mode of the Fabry-Perot cavity that gets activated. Okay, so this is how, this plot here actually shows, in the previous diagram, I was just showing that these are the allowed modes of the longitudinal of the cavity. Now, the question is, what is the width of these modes, right? Are these modes delta functions, or are these modes wide? So to do that, I can write the transfer function of this system, and it turns out that the transfer function of the system is decided by the R. Now this R is all this put together, all these things put together, I'm calling it as R. So for differing values of R, the phase condition tells you that the spacing is fixed, whereas the gain condition actually tells you whether the allowed modes are broad or whether the allowed modes are thin. So for instance, if R is very small, now remember what R is root R1 R2 e power minus 2 alpha d. It actually tells you that it's a very poor reflector. All the power is coming out. The reflected power is very poor, right? So for R is very small, the allowed modes are looking like this, which means that even if you pick one longitudinal mode out of the system, the width of the light that's coming out of that source could be large if there is spontaneous emission existing in the system. Whereas if your R is large, which means it's a cavity where the reflections are large, which means it could be something, I'll give you an example, maybe some 70% reflecting here, or maybe 80% reflecting and 90% reflecting, or 100. In fact, in ideal lasers, you will have one of them as 100% reflecting and the other one as 99% reflecting, so that this R is really large. And when the R becomes large, you see the allowed, it's the yellow line. The allowed longitudinal modes become extremely narrow. And why is it important to have this as narrow? Because it is this Fabry-Perot cavity which is acting as a wavelength filter for your laser. So even if there is spontaneous emission happening, it is going to pick only that spontaneous emission which is within this. This is in frequency or wavelength. So it is within this bandwidth of the Fabry-Perot cavity. Right? So the temporal coherence property of the laser actually is decided not just only by the spontaneous emission, it is also decided by the allowed width of the longitudinal modes supported by the laser. Now the spacing between the longitudinal modes is called as the free spectral range, or FSR, of the cavity. The width of the modes is decided by the cavity loss. Hence, the spectral width of the output of the laser is decided by the spontaneous emission. Of course, you need to have emission coming with all frequencies, and it's also decided by the quality of this resonator. By quality, I mean the value of R. Larger is the value of R, closer is it to 1, it means the quality factor of your resonator is really large, which means that the allowed frequency, the light that is emitted from this cavity is actually very narrow. I break here again to take the questions. There's a question by Neil. What is the unit Nipper? Oh, okay. So Nipper, I'll tell you what Nipper means. So you can represent gain or loss in different units. If I just say power output divided by power input. So let's say I have a system in which I have a certain input power and a certain output power. And let's say there is, I define gain or loss as power output by power input. That is just a linear unit. Okay. Now, you could also represent this as in a logarithmic scale by saying it is 10 logarithmic 10 in P out by P in. Then it is in dB scale, decibel scale. So you can very easily represent changes in orders of magnitude in decibel scale. Now the Nipper is where you can write P out is equal to P in times e power minus 2g into distance, where d is the length of this, whatever is that medium. In which case, P out, so this is the format. So this guy should not have any unit, right? But this distance has a unit of centimeter. So the unit of g should gain or loss, whatever it is. If it is gain, it is plus, right? If it is loss, it is minus. That should be per meter. And that Nipper unit will be the power of, in the power, if I have Nipper in the power of exponent, that will be dimensionless, right? So that is, when you say it is in Nipper per meter, you should understand that it is the gain per length, which is in the exponent. If I say it is dB, it means that it is just simply the ratio of output power to input power. So that was one question. Sachin has a question. What does a cavity consist of? Is it a vacuum or are there gases used? So the cavity typically depends on the laser. For example, if it is a semiconductor laser, it's just a semiconductor medium like this, right? And then the two ends of the medium are just polished and made as mirrors. So the entire medium is, entire cavity is the medium. It cannot be vacuum because the cavity, now remember, this is not the arm of the interferometer we are talking about. The arm of a interferometer, of a LIGO interferometer, has vacuum. But we are talking about the cavity, which is actually the laser, which means you need definitely it can't be vacuum because vacuum cannot emit light, right? So you need to have a medium which emits light. So the lasing medium is placed inside the cavity. Rahul has a question. Does zero crossing here mean wave 1 and 2 are crossing the x-axis in phase, or is it relevant? How can it change a CRO display in time if there's only one frequency? I will get back to that slide again because we have gone back and forth in that slide. So maybe towards the end, Rahul, I promise I will explain. Vaibhav, can you just mark that question to be taken once again? Why do we use different reflectors R1 and R2? Instead, can we use a spherical reflector which can have multiple reflections from all sides? Excellent question. So we don't have to use two different reflectors, and nobody said that it has to be two reflectors. It can be n reflectors. So in fact, that's my next slide, right? You have so this is the laser that we use in let me see if I can push this. This is a laser that is used in LIGO, which is a non-planar ring oscillator, which means that it is actually a single crystal, right? It's a NPRO laser, which is a single crystal, and the crystal acts as a gain medium. It also acts as a laser cavity, which means that, see, light enters this way. Okay, let me activate this pen. Okay, light enters this way. you see it has how many faces? 1, 2, 3, 4, 5, 6. It is a kind of a hexagonally cut crystal, and it is cut in such a way that enters this way. This face acts as a mirror first, and then it reflects, it goes to this face, it gets reflected here, and then comes back, right? And the way it is designed, the angle of the, so you see this is not at 90 degree, you have a certain angle. The angle is designed is such that the forward path and the return path are in different spatial paths. So this is how a LIGO laser is built. So you don't have two external mirrors. Now these two external mirrors are useful to explain how a laser works, but you can construct a cavity with 3 mirrors. You could have 4 mirrors. You could have entirely make it as a ring cavity, right? Fiber lasers are made of ring cavities, right? Or you could have a cavity like this, right? So most of these NPRO lasers are, so I hope that answered the question Sachin had. Yes, so the questions up to now are done, so we will move on. So those who are listening, please keep typing your questions so that we can take it up as and when you have that question. And so that, you know, you feel and I feel motivated to keep continuing. So this is the laser that that is used in all the LIGO installations today. These are what are, as I called, as NPRO lasers. This is made of this particular crystal, which is neodymium doped in garnet. It is yttrium aluminum garnet, right? And this gives a specific color. Now this Nd:YAG is used simply because the wavelength that this is one of the most popular materials, lasing materials, very, very reliable lasing material that has been used ever since the laser has been was invented. And this pumping is done again as an optical pumping, and that pumping is done at 808 nanometer, and the wavelength of emission is 1064 nanometer. So this is the wavelength at which all the LIGO lasers run. Now, a single block contains, as I explained earlier, 4 reflecting surfaces, and on the whole, the crystal looks as small as this. Somebody is actually holding it at his or her fingertip. The line width possible. So we said how the line width can be influenced by this cavity. So this cavity is so small that the entire path, so you see the polished faces here, these are the polished faces. The side faces are ground, so light cannot come out this way. Light enters this way, gets reflected from these 4 mirrors and comes out this way, right? And the size is so small that the spacing between the longitudinal modes is actually very large, so that it can work as a single longitudinal mode laser. And the possible line width, now how to define line width, I will tell you a little later, but that is about 1 kilohertz or less than 1 kilohertz. Next question, why study laser phase noise? So this is a laser. We know that the laser is giving you a nice coherent light. Why bother studying about the noise? Especially because, so this is the picture I have taken from Ivan Hall's LIGO thesis from Caltech. So this is again a simplistic picture of the interferometer. So the light comes here, it goes, reflects back, and you make your observations in the detector, which is the antisymmetric port of your interferometer. The round trip phase of each arm is 2 omega naught Lx and 2 omega naught Ly divided by C, because you are relying, let's say one arm, you call it as the phase phi x, the other arm, you call the round trip phase of the light as phi y. And you have quantified this 2. And you're relying your measurements on based on the fact that the Lx and Ly are going to change whenever there is a gravitational wave propagating. Now, if you look at the intensity or the electric field at this antisymmetric port, EAS, is E naught by 2 exponential phi x minus exponential phi y. It's just a simple interferometer equation that gets written here. Now, you can take out phi x outside, phi x plus phi y by 2 outside, and then you can immediately realize this is exponential e power I phi plus sine of phi minus, which means that my power, which is mod of EAS square, right? When you do a modulus, this I goes away, you have mod, you have E naught square, This also goes away. What remains is just sine square phi minus, right? Which means that the power that you are observing with the detector always detects power. It cannot detect field. A regular detector detects power, right? So that is dependent only on phi minus, which is actually the difference. Phi minus is nothing but, phi minus is nothing but phi x minus phi y divided by 2. It is dependent only on the differential phase. Now, the light is coherent, which means that there is a perfect correlation between the light that is going and coming back here and between the two arms. It is spatially coherent, it is temporally coherent. So there are no fluctuations because of the laser. And you're looking only at the dark port. So you're interested only in the differential phase. Any common mode phase. Now, what is this common mode phase? If the laser has some phase fluctuation, that will be common to these two, right? So that common mode phase is not appearing in your detection at all. Then why am I worried about laser phase noise or intensity noise? It should not affect my measurement, right? Because you're making the measurement in the dark port. So the answer is the common mode rejection is actually very small. The rejection between the two. So depending on how this interferometer is set up, it is only a factor of 100 that you get by this common mode rejection, which means that there is still an influence of there is still an influence of the intensity noise and the phase noise, even though they are common between each other. The visibility of that is only very small, and only you get only the only a fraction of 100 improvement because of the common mode rejection. So to give you an idea, in order to have a negligible contribution to common mode noise, the laser phase noise should be this. I'll tell you how this unit comes about, but for now you just understand that take this number 10 power minus 8 radian per square root hertz at 100 hertz. So this at 100 hertz means if this is the carrier frequency of the laser, so this is the laser frequency at a frequency offset of 100 hertz from the so this 100 hertz is this separation at a frequency offset of 100 hertz. The phase noise is supposed to be 10 power minus 8 radians per square root hertz. Whereas if I take the NDAG NPRO laser that I showed you earlier, the free running NPRO laser, even though it is made with a single monolithic cavity, so there's nothing vibrating in that system, there's absolutely nothing changing in the system. Its phase noise is 1 radian per root hertz at 100 hertz. So we have a difference of order of magnitude of 10 power 8, which means that the laser that we have is actually 10 power 8 times worse than what is expected. So that is simply because, the common mode, if this common mode rejection idea was correct, it should not have mattered. So it simply means that even though we do have a common mode rejection, even though in the first principle says that you should not have any common mode noise, the rejection that you get is very poor, which means you have no other way but to improve the laser quality and do something to make the laser much, much more monochromatic than what it is. Right? So that is why we need to study the laser phase noise. There's a question that has come up from the previous section. Why is the pumping frequency different from the emission frequency? Okay, so there are lasing systems where the pumping frequency is the same as emission frequency, but in NDAG, what happens is, you see, as I said, there is a metastable state which is required, a state which has a higher, larger lifetime, which is required for lasing, and that is your lasing wavelength. And 808 is actually a higher wavelength where this absorption coefficient of the crystal is high at this 808 wavelength. So if you So there is always a absorption coefficient and an emission ability of the crystal to absorb, ability of the crystal to emit. So there's also always a absorption coefficient and emission coefficient for any given material. Turns out that at 808 the absorption coefficient is very high. At 1064 the absorption is not very high, but the emission is very high. So the trick is to actually pump it at a higher energy state. The ions de-excite, the neodymium ions de-excite to this state, and this is your 1064 emission state. This is through a non-radiative process. Okay, so depending on the laser material, you can choose, depending on the emission and absorption properties of the material, the pumping wavelength is chosen. So that is the end of that question. So we will move on. So I think we are convinced that we should study about laser phase noise. The example for noise budget is something like this. Full noise budget is from a 2003 demonstration from Rana Adhikari's PhD thesis is here. You see that there are several sources of noise which counters the detection limits of the LIGO laser, of which I can point out that, okay, let me use a different color here. I can point out that, for instance, okay, this graph itself is colorful. You see here, there is something called as laser intensity noise, and then there is something called as laser frequency noise, right? So one of these yellow lines is the laser intensity noise. So maybe this line is the laser intensity noise. And the other green line, there is a green line here, and that could be the laser frequency noise. So these two contribute to the noise in the laser, which contributes to the sensitivity of detection. And we are interested in the sensitivity in the range of 100 to 1000 hertz, because that is where all these gravitational wave events are located. So you want a very large sensitivity there, which means the noise there should be really low so that you can detect the slightest of the gravitational wave signature. Okay. Noise in laser sources. So I have a question to Vaibhav. It's almost going to be 5 o'clock. Should I continue, or should I do this as a rest of it as a part 2 of the lecture series? Okay, Samir says continue. Continue for how long, Samir? Okay, continue for 15 minutes, and maybe if it's not getting completed, we can do a part 2. Thanks, Samir. Now, how do you now quantify the noise in laser sources? Okay, so we need to first quantify, and then we need to see how to measure it. Now, quantifying, we will again rely on mathematics, right? So we define it mathematically, and then we can, see how to do a measurement. So electric field at the output of the laser, you can say that it is intensity noise, can be quantified as the electric field is amplitude and phase. And the amplitude is actually square root of power. And phase is, of course, e power j omega t plus phi of t. Now, power, the fluctuations in power. Okay, I have an interesting question here coming up. Sachin says, does laser noise really affects the gravitational waves? And the answer is absolutely yes. If affected, so what are the alternatives to remove or improve it? That's what we are trying to do. So we are trying to first quantify it. We are trying to measure it. And then later on, we will see how to remove it. Because to remove it, I should know how much is it, right? And to know how much is it, I have to make a measurement. And to make a measurement, I should know what should I measure. So that's why we will first start to quantify the noise. Then we will try to see how to measure it. And later we will see how to control it. I can tell you that LIGO has been one of the biggest challenges for the laser community. I belong to a community where I do not do gravitational wave physics. I don't do any relativity or any such thing, any astronomy. I am completely, my research is all on lasers and on narrow line lasers, especially for communications, optical communications. In fact, my area is optical coherent communication, where we use the phase to encode information. But I can tell you that the laser for LIGO has put a big challenge to our community of lasers, to generate a laser which has not just very narrow line width. It also needs to have, it needs to be very silent at specific frequency ranges, because you want to detect your gravity waves which are of specific frequencies. At those frequencies, you want your noise of the laser to be extremely narrow. And that's a big challenge to our community. For 1064, we are doing things like, we first of all take a single monolithic crystal, and beyond that, we try to lock it to a very silent cavity and things like that. But in the advanced LIGO and even in the futuristic LIGO installations, what is preferred is we need to move from 1064 nanometer laser to either 1550 nanometer or 2 micron to reduce the overall noise of the system. And there are no lasers yet which are, or I would say that they are still being researched to make it LIGO quality. So our research is also to build a laser in 1550 nanometer and 2 micrometer whose quality is LIGO class. And that's a big challenge for the laser community. Okay. So the way to quantify intensity noise is to say that, so what is this intensity noise? If you measure the power at the output of the laser, let's say it's a 10 milliwatt laser, you have 10 milliwatt, you expect that it's a continuous power, but what you actually see is that some fluctuations around this. So this is as a function of time. If you keep measuring the power, you will keep seeing some noise around this, right? And when that happens, you need to quantify the noise, whether it is small or whether it is something like this, where you have the fluctuations are really large, right? So the way to quantify is that you say that this power is average value plus a deviation, which is nothing but the standard deviation of the histogram when you draw the histogram, right? So all these power values you accumulate, you keep measuring the power as a function of time, you accumulate all that, you draw a histogram, find the fit it to a Gaussian, it will fit to a Gaussian, and find the variance and standard deviation of that. That gives you this delta PT. Okay, and obviously for the brown laser, the histogram is going to be a little more narrow, so the noise is going to be narrow. So relative intensity noise is the ratio of this standard deviation of these fluctuations divided by the average value. That's a very simple definition, right? If the ring is large, it means that the power is fluctuating much more, and the ring is small, it is fluctuating less. The other way to quantify noise in the laser is phase noise, where you say that the phase is fluctuating with time. So the phase is phi naught plus a delta phi of t, where this phi naught is some random initial phase. The consequence, as we discussed earlier, is that when you have a phase that is changing with time, so let me come back to that point where Rahul had a question. If the phase is continuously changing with time, different waves, if I superpose, they are coming like this, it simply means that there is a phase fluctuation. At a given point, if I measure time, the phase is actually fluctuating. So it means that if I calculate the instantaneous frequency, which is the first derivative of this is, so you have omega ct plus phi of t is your instantaneous phase. So the frequency is the first derivative, which is omega c plus d phi by dt, right? Now, if this d phi by dt is not a constant with respect to time, it means that you will have the instantaneous frequency keeping continuously changing as a function of time. And that gives rise to the phase noise of the laser. Now, if it's a semiconductor laser, you have, there is a coupling mechanism by which the intensity noise actually gets converted to, phase noise, right? but not for NPRO lasers. So we move on to intensity noise. The reason for intensity noise is again spontaneous emission. There could be pump fluctuations, so there could be carrier density fluctuations, and so on. The RMS value of intensity noise, as I said earlier, will quantify the fluctuation. I keep on saying intensity noise, but actually we are measuring power. So that's again to do with the traditional definition for this noise. I mean, power and intensity are proportional to each other. So we keep on saying intensity, but we keep writing power here. And I think that is acceptable. But what is also interesting is to find out whether these fluctuations are slow or fast, which means that suppose I take the power fluctuations, right? The standard deviation could be the same, but do I have power which is fluctuating very fast, or is the power fluctuating very slowly? Both of that could give the same standard deviation, right? So there is also this concept of frequency involved in these fluctuations. Right. So these fluctuations could be, you also want to know whether what is the frequency of these fluctuations. And why is that important? Because if your fluctuations are at the same frequency as that of your gravitational wave, it means that this fluctuation is going to interfere with your measurement. Right. So in all these noises, you need to quantify the frequency spectrum of the noise. Right. And the fluctuations, as I said, is slow or fast, and the registration, it should depend. And how you're registering these fluctuations, you're using a detector of, let's say, a bandwidth of 100 megahertz. It means that you can record fluctuations only up to 100 megahertz. If there are faster fluctuations, the detector is not simply detecting it. So fast fluctuations may not be detected by a slow detector. Now, in case of slow fluctuations, what happens? The other limitation is the limited measurement time. Let's say my fluctuation is at 0.001 hertz, right? Which means that I have 1,000 seconds after which only I'm seeing a fluctuation. And if I did not make a measurement for 1,000 seconds, I've missed that fluctuation. Right? So it is actually a trade-off, right? You need to know, you need to choose the right bandwidth for the detector, and you also need to choose the right integration time for these measurements, right? Both will affect your measurements. So it is actually better quantified through power spectral density. And so what is power spectral density? Power spectral density is nothing but the Fourier transform of autocorrelation function of the power fluctuations. So if I have power fluctuations, let's say this is my power. First of all, you normalize it, so you make it 1. And then around that, you measure the fluctuations, right? You have a time trace of your fluctuations. What you do is, of this time trace, you calculate the autocorrelation. Just a primer on autocorrelation. If this is the function, this is a famous Wikipedia picture. Autocorrelation simply shifts this waveform in time and keeps changing the delay between the shifted version and the original waveform, right? So this is what it is. So this is the shifted version and this is the original waveform. If they are not overlapping, the autocorrelation is 0. As this shifted version keeps moving across this original waveform, the autocorrelation answer goes on increasing, and when it becomes maximum, the autocorrelation answer is maximum, and as it moves out, the autocorrelation answer becomes less. The power spectral density of these fluctuations is actually the Fourier transform of this autocorrelation, which means that if this autocorrelation is narrow, the Fourier transform of this is going to be very wide. Now you can take a guess. If my laser is fluctuating, having very fast fluctuations, which means that there are a lot of frequency contents in the fluctuation, would my autocorrelation be narrow or wide? Think about it. My question is, if my laser is poorly correlated, right? Would my autocorrelation be narrow or wide? And would my fluctuations be, would my power spectral density be narrow or wide? So I'll give you the answer. If it's in any random process, this is a very slowly fluctuating process. So if I take a delayed version of this and take this multiplication, I will see that this is correlated for a long delay, so the autocorrelation is really broad, and so the power spectral density is narrow. You know the inverse relation between the time domain and frequency domain. Broader is in the time domain, narrower is in the frequency domain. But if I have something really fluctuating very fast, it means that it loses its time correlation very fast, which means that if I delay it slightly, if I delay this function slightly away, there is no product that is coming. The product reduces, the autocorrelation product falls to low value even at small delays. And such cases, the power spectral density becomes broad. So this is to intuitively tell you that if your fluctuations are very rapid, the random process is very rapid, the autocorrelation becomes narrow, power spectral density is actually broad. Now, so this is the mathematics of it. So this is the autocorrelation operation. So this is multiplication and summation. And this is the power spectral density, which is the Fourier transform of the whole thing. And how do I now get the delta P, which was my RMS value? So you integrate this over the range of frequencies that you are interested in, take the square root of that, that will give you delta P by P. Right? So this is the math explaining the process. It is experimentally measured this way. So you take the laser, you attenuate the laser so that it doesn't saturate the detector. You allow it to fall on a detector, and the detector should be such that its noise level, its noise sensitivity is very low, so that the noise of the detector is not affecting your measurement. It is taken through a low noise amplifier and fed to an electrical spectrum analyzer. Right? The noise floor again of the spectrum analyzer should be smaller than that of the detector. Otherwise, you are measuring the noise of the detector, of the spectrum analyzer. So noise floor of the spectrum analyzer should be smaller than that of the detector, should be smaller than that of the laser. This is the precondition. It is measured in per hertz. Some people measure it in per root hertz, or you can measure it in dBc, which means dB value relative to the carrier in per hertz. Now, the way this per root hertz is written is, you generate the noise, you measure the noise, and you would have used a detector of a certain bandwidth B. So you divide this by the square root of the bandwidth, and that's how you get it as per root hertz. Right? Now, the question about stabilization, somebody asked a question about stabilization. Stabilization is definitely carried out in LIGO lasers to reduce the ring. So to give you an example, this is an example from a paper which is talking about solid state stabilization for LIGO lasers. So you see here this yellow light, which is yellow line, which is masked by this picture. This is how the unstabilized ring spectra is. Right? So you asked me a question, does the laser noise affect the detection? You see the black line is where the requirement is. So if you really don't do anything about it, you're not going to be able to detect anything in the advanced LIGO experiments, because the laser phase noise, laser intensity noise is really high. What is usually done is you take the laser and use this to stabilize it against a cavity, which could be the interferometer cavity itself, and give a feedback to the laser so that if there is any power fluctuation, that is kind of stabilized. So that is taken care by the control systems. Right? So we are not going to be talking about those control systems here, but that's a very interesting control system which stabilizes the power of the laser. Now you see that this is where you have a free running noise, and these are some short noise, which is the electronic, the photon noise. This green is the electronic noise of the detection, right? This is important to know where are the total limits. And you see the total noise of this laser they have measured in the pink line. And what they claim here is that this is, of course, meeting the requirement of the advanced LIGO. Right? So I think we stop here at the intensity noise, and if there is sufficient interest, maybe you can give a feedback. We can have another talk based on the availability of slots for discussing the phase noise of the laser. Before I conclude, let me just come to one slide here. Just to tell you that we are at IIT Madras, we are involved in LIGO training and R&D. The areas that we are working on are this kilohertz class, kilohertz class lasers. We are trying to measure, first of all, accurately and make these lasers for wavelengths that are not 1064, but at different wavelengths which the LIGO Voyager and advanced LIGOs are demanding. We are also making the fiber laser. So it is not just enough to produce a laser of narrow line width, you need to be making it at high power also, right? So that's an additional challenge. So we're trying to build fiber lasers for that. We are also working on speckle correlated optical levers, which will help in mirror alignments. There is a group working on advanced controls, so which will also include the laser control. And there's a group in mechanical engineering which is trying to do seismic isolation using phononic band structures. So they try to say that if you put certain structures in a certain pattern around the LIGO installation, the environmental noise, the ground noise, etc., can be minimized. And of course, thank you for listening to me. Of course, we did not finish what I had intended to, but I think whatever, it's not important to cover everything, but it's to uncover some of the ideas. And we can always meet again if there is an opportunity. Thank you. I have a question here. There's no more question. And the next talk, next episode in the series is by Dr. Saurav Chatterjee on astrophysical origins of merging binary black holes. And that is on 27th, Monday. Thank you very much. Be happy to take any questions. So I have a question which says that while detection, can we use one more detector to minimize the noise and then pass it to the forward detector? Unfortunately, noise is something that once it is included in the measurement, you cannot remove it. Anything common mode can be cancelled, but the cancellation that you can achieve for common mode is actually minimized. That's what I told you earlier. So the idea would be to not have the noise. Once you detect it, you have it already, and then removing it is a big challenge. Of course, in communication systems, people, for example, in your GPS signal, right, you have a very weak signal that is coming to your cell phone, and that's buried in noise. You're able to detect it. That's because that's coded, right? Your phone is expecting a certain kind of signal. You can do cross correlations, etc., and you can basically code your signal such that it has good correlation properties, and from the noise you can extract your signal out. But gravitational waves are not coming coded. You have to detect them as they are. You don't have the liberty to play around with the nature of that signal so that you can do some kind of coding. Right? So of course, there are lots of algorithms that are being developed to still figure out the signature of the gravitational waves from the noise. But the idea when you build a detector is to have a, so this is the way it works. It works in the reverse way. You want to detect certain events, and then you say, okay, this is the strain sensitivity that I need to detect this event. And to be able to get this strain sensitivity, my noise should be lower than this, and of which the contribution from the laser noise should be lower than this, right? So then that's the target for the laser. And then the laser folks will start building the laser and controlling it so that the measured noise is less than what is the required. The other big challenge here is how do you measure it accurately? The noise levels are so small that what is to say that your measurement is right. So at the moment, we are trying to spend a lot of time in our lab to understand how to validate our measurements, right? Because it's a very, very stringent requirement. Is there any literature you can share on machine learning algorithms for identifying and reducing laser phase noise? Well, machine learning algorithms are indeed used for control. Of course, there is a lot of literature available. We can possibly share them as well. Any other questions? There was one question I said I will. I think I covered it later, which was marked in red. I think we did that. Um, Crossing the x-axis is just a way to intuitively understand. Ultimately, the point is that phi of t changes as a function of time. So this d phi by dt has multiple values, and so you have a frequency spread. Uh, Anything else? Okay, there are no more questions. Thank you very much. I enjoyed talking to you. It's a very different experience. I hope you had a good time as well. Thank you.